Hello, and welcome to Chapter 6, Section 2, where we're talking about more confidence intervals today. So today's section is really similar to the one we just did, where we're still looking at confidence intervals for the mean, where we're trying to estimate the population mean, but this time we don't know what that population standard deviation is. So that's what the sigma stands for. So last section, the population standard deviation was just given to you. Now, in this section, the population standard deviation is not given to you. Instead, you only know the sample standard deviation. And this is actually much more realistic, much more used in real life, because in real life, it's not very likely that you're going to know the population standard deviation. What it might say is that, they'll tell you, in previous studies, we found the standard deviation to be this. And that's kind of more used to be the population standard deviation versus just, here's our sample that we're using in our study. This was the standard deviation in it. And so it's much more likely that you're just going to have a study where you find the standard deviation from that sample in the study. So a few things change because we don't have a population standard deviation. We don't really get to use that normal curve anymore. It's still kind of normal-ish. It's just called the t-distribution instead. So this t-distribution kind of has a normal shape. But the weird thing about it is that the shape actually changes as your sample size changes. When your sample size is small, like less than 10, it's actually like imagine like the normal curve but kind of smushed together, then like kind of flatter and squished down. That's the shape that it takes on when your sample size is small. If your sample size is like around 20-ish, which isn't like a super large sample size, but not small either, then it's less smushed. And then as we get to sample sizes that are 30 or greater, so this is considered a large sample size. When you are doing a study and you are using lots more people within your study, then the shape of that t-distribution actually changes to more of a normal shape. So this is like the normal curve. So one more thing that I want to tell you about involving the t-distribution is this thing called DF. It stands for degrees of freedom, and there's a formula to it. It's n-1. So this is the number that actually determines the shape of the t-distribution. And when you look at the table, this is why you'll need it. So before we go into using an actual example, I want you to see the table first. So it looks like this is the top of it. So you see the shape of it, kind of normal shaped. Just the picture is a little bit different than what you're used to from the normal curve picture. So here they have it so that they have the tail probability. We're really only looking at like what is on the ends. And it always used to be shaded to the left. This one, it actually doesn't matter. This one has it shaded to the right, but really it also works for shading to the left as well. Because when you look at the table itself, in the middle, all these numbers, they're not percentages anymore. So all of these values here are actually the TC values. So last section, we had to calculate ZC. So for the t-distribution, it's called a TC number, that critical value. And on the side here, you'll see the DF, the degrees of freedom. So this is how you're going to look at what row to use based on your sample size, because the degrees of freedom is that n-1 number. Okay, let's do an example so we can see how to use this table. So we're going to find TC if C equals 0.95 and N equals 15. So C equals 0.95 means this is a confidence level of 0.95. So for 95% confidence and N equals 15, then on a table we need to figure out where 95% confidence is. And then we are using the row for the DF, which is n-1. So we're pretty good at math here. 15 minus 1 is 14. So that's going to be the row that we're looking at, and we're looking for a 95% confidence. So with this table, it's actually way easier. With this table, all the way down, it says confidence level C. They already list them all out for you. So if we want 95% confidence, we just look for 95%. And then we go up until we have the degrees of freedom that we want. So crisscross it with 14, because we said the degrees of freedom was 14. Crisscrossed with the 95% will give us this 2.145. So TC will be 2.145. That's it. I want to do one more example with you. Because this time I want to use n equals 44, and we're using a confidence level of 90%, so 0.90. So using my table, then I know the degrees of freedom is going to be 43, because 44 minus 1 is 43. And if the confidence level is 90%, then when I look at the table, I'm going to look down until I see 90%, and then up until I see 43. But 43 as a degrees of freedom is not on there. Awkward. So when you look at the degrees of freedom, 43 is in between 40 and 50, and that's all that they give us. So if they don't give you the actual number that you need for the degrees of freedom, always round down. Because if you round up to 50, then it's kind of like you're lying about your sample size, and lying about a larger sample size is actually bad because you're basically claiming more accuracy than you actually have. And so if we round down, then we're just being more conservative, and this is actually better because you're not really lying. You're like lying about a lesser evil, I guess. So we always round down because you're not claiming to be more accurate than you really are. All right, so in this case, we would have to use degrees of freedom of 40 because the 43 doesn't exist on the table, but we're still looking at the 90% confidence. So for 40 and 90% would be right here, 1.684 would be our TC. All right, so now that we know how to calculate or find the critical value, the TC, then we can plug into our confidence interval formula to find the entire confidence interval now. So the formula looks like this. We have X bar, which is that sample mean, and then we're going to add and subtract, so plus or minus that TC that we would know how to find now, times S over the square root of N. And remember, S, we said earlier, was the sample standard deviation. Okay, so let's do an example to test this out. So in this example, we've got randomly select 16 coffee shops, measure the temperature of the coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Find the 95% confidence interval for the mean temperature. Assume the temperatures are approximately distributed. So they're telling us it's going to be almost a normal curve. They want a 95% confidence interval. They tell us the mean and the standard deviation. It also very clearly says it's a sample standard deviation. So that means we have to use the TC. Okay, so I'm just going to list out some numbers on the side that they're telling me. So N is 16 because they told me there's 16 coffee shops. The mean, so the X bar, would be 162.0. S, our sample standard deviation, is 10. And then now that we know these things, we can plug in, or we can find TC using our sample size of 16. So the degrees of freedom would be 15. And then 95% confidence. So using our table again, 95% confidence. Degrees of freedom of 15 would be right here of 2.131. So now we can plug into our confidence interval formula. So sample mean 162 plus or minus 2.131 times S was 10 over the square root of N. So make sure here, a common mistake is people always forget and they use the degrees of freedom here instead of N. Remember, N is 16, degrees of freedom is just used to look at the table. All right, so plugging into our calculator, when we subtract 162 minus 2.131 times all that stuff, we end up with 156.6725. And when we add, we end up with 167.3275. Okay, I'm just going to leave a bunch of decimals, it's fine. Alrighty, so there's our confidence interval. So we're basically saying we're pretty confident, we're 95% confident, that that temperature for the average coffee sold is going to be between these two numbers, which is pretty hot. I used to work at Starbucks, and like 170 was considered extra hot. Like if you asked for a drink that was extra hot. And then kids temp was 140. So this is like pretty standard temperature for a coffee. All right, so now the real challenge between these two sections that you've done is just being able to tell when to use which one. So when you read a question, you want to make sure the difference between the two is what kind of standard deviation are you given. That's the main thing you're reading for. So as you read through the problem, be real careful which one's talking about a sample, which one's talking about a population. In this problem, we say randomly selected 25 newly constructed houses. The sample mean construction cost is $181,000. So here they're saying sample mean, but we don't care about the mean when we're trying to decide which one to use. We only care about the standard deviation. The population standard deviation is $28,000. So right here, when they talk about the standard deviation, they're saying it comes from a population. So right there, that's when you know you're given the population standard deviation. So between the normal distribution, the t-distribution, or neither, this should be the normal distribution. So if you want to think about it as like using a ZC for this problem, that's how we're going to tell. So remember, population standard deviation is when you use ZC. TC is when it's a sample standard deviation. Neither would be like if you didn't have a standard deviation at all. That's it for this section. Thanks for watching. Don't forget to like and subscribe, and we'll talk to you next time. Bye.